Mask control, spatio-temporal control for masked motion synthesis. Text-to-motion modeling is an emerging research area that generates semantically rich human motions from textual descriptions. Human motion here refers to the movement of the human skeleton. Beyond textual descriptions, what if we want to explicitly control each joint? Current controllable motion models utilize ControlNet plus guided diffusion to control joint positions. However, they often exhibit low precision and generate unnatural motion. We present mask control, which can achieve high quality and high precision, while supporting a wide range of applications. There are three main approaches to human motion generation. 1. Diffusion models, denoising processes. 2. Autoregressive models, predict the next motion token step by step. 3. Masked models, predict multiple motion tokens simultaneously. The first is the diffusion model. It's versatile because it operates in continuous space, allowing flexible downstream applications since the continuous motion space is easily manipulable. However, the downside is that it's slow and less precise. The second is the autoregressive model. It can generate a flexible range by prediction n token, but since it works in discrete space, quantized tokens, it's hard to control. The last one, the masked model, produces high quality and fast generation. But, like the autoregressive model, it also operates in discrete space, making control challenging. Most controllable motion models rely on diffusion models. But what if we can make the masked motion model controllable? Since it already achieves high quality and fast generation. Let's first look at the background of the masked motion model, MMM. It consists of two components. One motion tokenizer, VQVAE. The encoder takes motion data and compresses it into a continuous latent representation. Instead of keeping the continuous values, these latent vectors are quantized by replacing them with the nearest vector from a learned discrete codebook. The decoder then reconstructs the motion from these quantized embeddings. 2. Masked transformer. The motion tokens are randomly masked, and the transformer is trained to predict the missing tokens from the visible ones, similar to masked image modeling or BERT. During inference, it starts with all tokens masked, and gradually unmasks them by selecting the highest probability tokens until all tokens are predicted. Unlike motion diffusion models that operate directly in continuous motion space, the masked motion model encodes and quantizes different types of motion data into a discrete latent space. This has several advantages. First, the error correction from vector quantization. Next, the unmasking process selects the highest probability token and leaves the low probability token for the next prediction. However, these are also the limitations of masked motion model. Discrete tokens cannot be smoothly adjusted by small perturbations. Can we control these discrete tokens in masked motion models? Yes, we can. We do so by treating discrete tokens as continuous by relaxing quantization. Our mask control model has two main components. 1. Logits Regularizer, a ControlNet-style module. 2. Logits Optimization, a latent space optimization applied at inference time. Both manipulate logits, rather than embeddings directly. Let's start with the Logits Regularizer. ControlNet-style conditioning on control signals. This module is a trainable copy of the frozen mask transformer, connected through zero convolution. However, unlike the original ControlNet that operates in continuous diffusion space, the masked model predicts the probability distribution over discrete tokens and then selects one via the argmax operator. This categorical selection is non-differentiable, so the categorical tokens cannot be directly controlled by continuous signals. To solve this, we propose differentiable expectation sampling, which relaxes the quantization constraint. The masked transformer outputs logits. Instead of taking the argmax and picking a single codebook embedding, we apply softmax to get the probability distribution of the whole codebook and compute a weighted average of codebook embeddings, effectively approximating a continuous embedding. We also add Gumbel noise to introduce categorical variation. Surprisingly, this simple trick works and makes categorical data controllable. We trained a model with two losses. Cross-entropy loss, from the original masked model. Reconstruction loss, forcing that generated motion to match the target control signals. The second component is Logits Optimization. A test time optimization applied at each unmasking step. However, we again face the non-differentiability of categorical data. Moreover, we also need to convert between the transformer's learnable token space and the codebook embedding space for reconstruction, then backpropagate gradients through back to transformer's learnable token. To solve these problems, again, we utilize differentiable expectation sampling, which relaxing quantization constraint by calculating the expectation of the codebook. To convert between different spaces, we simply apply expectation sampling to each space, optimize through the logits, and then reconstruct back to the transformer's learnable tokens to generate motion for the next unmasking step. Here's a visualization. On the left, no control. In the middle, Logits optimization only. The motion is accurately controlled but drifts toward the end. On the right, combining Logits optimization and Logits regularization gives precise and high-quality control. Compared to methods like Motion GMD, Motion LCM, and OmniControl, those models show imprecise control and unnatural motion. On the right, our MaskControl achieves both precise control and natural motion. Here are more results in video form. The above one is generated from text, a person walks in a circle clockwise. On the bottom the text is, a person walks forward and waves his hands. When plotting FID score, lower is better, against average control error, also lower is better. Our MaskControl lies closest to the bottom left, showing the best trade-off between quality and control accuracy. Because Logits optimization is applied at inference, it can incorporate any arbitrary objective function. This supports a wide range of applications. For example, obstacle avoidance, by applying a signed distance function, SDF, loss. Spatial restriction, by constraining motion to remain inside a box-shaped region. Body part timeline control, allows different body parts to follow different textual descriptions. And in human-object interaction, we can adjust the size of the object that the hands interact with. Thank you for your attention. For more details, please visit our website.